Awesome. All right, I'm Cathie. I'm going to tell you about R1CS and smart contracts with Bulletproofs. So I currently work at Interstellar, previously Chain. Cool. So this is a general roadmap of what I'll talk about today. So everything is sort of based on the Bulletproofs paper, which is this paper that came out about 1.5 years ago. That's basically a new zero-knowledge proof protocol that allows for no trusted setup and some other nice properties. So I'm not going to talk too much about the paper, but I'll talk about the range proofs that we built over this protocol, and then the constraint system proofs. And then I'll talk about how we use the constraint system proof protocol to make a confidential assets protocol, as well as what we're currently working on, which is a zero-knowledge smart contract language. And this lower right-hand side box is sort of an indication that there are a lot of other things that you can build with this constraint system proof, and it's sort of, an open ground for everyone to develop on. Cool, so this is a nice illustration of the Bulletproofs range proof by Oleg, who is our graphics mastermind. And as you can tell from the upper left side, you basically want to prove a statement that a value v is in a range 0 to 2 to the n. And then you go and break that into 3 separate statements, and then you add blinding factors and combine those statements, so on and so forth, until you end up in an inner product proof. And then you make a proof for that whole thing. So we implemented that, actually, thanks to a lot of the zero-knowledge proof tools that Henry made. It was actually really fun and easy to implement, and really performant as well. So these are R and performance numbers for the Bulletproofs range proofs. It's currently the fastest implementation and all in Rust. So that was really fun. But probably what you are more curious to hear about is the R1CS proofs. Let's see. There we go. In my presentation, anytime I say constraint system, really what I mean is rank 1 constraint system. It just sounds a little easier to say. And so I'll explain what they are and an example of how to use them. So in the bulletproof constraints, or the bulletproof sort of setup, there's 2 kinds of constraints that we have. We have a multiplicative constraint, which is a combination of 2 secrets multiplied together equals a 3rd secret. And then another kind of constraint is a linear constraint, which is just a linear combination of secret variables with clear text weights. And the assumption when you add a linear constraint is that that whole thing equals 0. So that's what we're working with. And the reason that we want to use a constraint system in R1CS is that, first of all, you can efficiently represent basically any efficiently verifiable program in R1CS. And then an additional reason we chose this is because in the Bulletproofs paper, it actually defines your whole statement using an arithmetic circuit, but it's sort of hard to work with arithmetic circuits and allocate multipliers, and you just sort of all you're working with is a giant matrix that's kind of clunky. And so we just use the R1CS abstraction to make it easier to work with, and that actually simplifies, sort of compiles down to an arithmetic circuit pretty trivially. So yeah, when we're making a constraint system proof, we're making a proof that all of the constraints are satisfied by certain secret inputs. So that's basically what we were working with coming from the paper. And as we were implementing the constraint system proof, one thing that we realized is that it would actually be really, really nice if we could use challenges, if we could make the generation of the statement that we're trying to prove interactive. And the nice thing about Bulletproofs is that there's no trusted setup. And so because there's no trusted setup, you can actually create a circuit, select a circuit from a family parameterized by challenges. What that means in practice is that you can commit to variables in Bulletproofs, so high-level variables, low-level variables, make a commitment, and then you can get random challenge scalars from that commitment. So this is really nice because it allows us to make smaller and more efficient constraint systems. So I'm going to walk through later in my presentation an example of a constraint system that is made much more efficient, the shuffle, using the challenges. And one thing that I just wanted to point out for people who are like theory of computation nerds is that this is really cool because when you have a normal like non-interactive proof that is reducible from anything that is NP complete, but when you make it interactive using the challenge protocol, you can actually, then it represents or is reducible from a larger space, which is now P space. So that's fun. In practice, we actually don't have a great idea of what this means, and it's, under research. So it's just fun. Cool. So let's walk through an example that hopefully illustrates the API and the shuffle extension. So we want to make a proof that the inputs and the outputs to a little box are a random shuffling of each other. And so in this case where you have 2 inputs and 2 outputs, your only allowed states are A equals C and B equals D, or A equals D, B equals C. And this can be generalized to more inputs and outputs, obviously. So there's many ways that you can do this, but one way that we can do it really efficiently using a challenge is to use equality of polynomials when roots are permuted. So you get this challenge scalar x that you actually get after you commit to A, B, C, and D. Then you make this equation, a minus x times b minus x equals c minus x times d minus x. And this equation is true if and only if c and d are a valid permutation of a and b. So that's really nice, and you can see how this generalizes to more inputs and more outputs. And then, a thought exercise, you can try to come up with ways that you could do this without using a challenge, and it actually requires a much larger circuit and many more constraints. So here is just an example of how we'd allocate those constraints within the constraint system. So this is actually like code that works, and you can run through this. Run the tests on this on the GitHub repo. So this function takes in a constraint system, and it takes in the variables A, B, C, and D. It then sort of transitions to a state that allows you to get challenges, and it calls on line 6 cs.challengeScalar. And when it's calling that, it's actually calling the transcript instance that is held onto by the CS, the constraint system, to reference what Henry was talking about with transcripts being really nice and easy to use. So you just set x as the challenge scalar that comes out of that transcript. And then on line 8, you allocate a multiplier by calling cs.multiply, and you pass in 2 linear combinations, a minus x and b minus x. That allocates a multiplication that gives you sort of 3 variables back. We only care about the variable that represents a minus x times b minus x, and we call that input mul. And then we do that again on line 10, so we say c minus x times d minus x equals output mul. And then on line 12, we say input mul minus output mul equals 0. And so altogether, these 3 constraints give you a minus x times b minus x equals c minus x times d minus x. And it constrains the relationship between a, b, c, and d using these 3 constraints. So that's pretty cool. It's actually hopefully really straightforward. Each call is one constraint. And the way that you use this is you have to obviously make a prover and a verifier for this proof system. So the prover has the secret scalars that represent A, B, C, and D. And in this example, we're just using an RNG to generate the random blinding factors. But when you're using this in practice, you could pass in the blinding factors yourself into this commit statement. So in line 6 through 9, you're committing to these A, B, C, and D and blinding factors and getting back commitments to them and high-level variables that are allocated within the constraint system. And then you pass these high-level variables into this toShuffle function, which is the function we saw on the last slide, as well as your prover constraint system. So this toShuffle function, as we saw, basically adds constraints over these variables in the prover constraint system and modifies the constraint system such that when you call let proof equals prover.prove, you get a proof back of the validity of these variables given those constraints. So that's actually it. And then on the verifier side, you do something very similar. You also allocate, you also make a new verifier constraint system up top, and then you commit to the A, B, C, and D commitments. So the difference between the prover and the verifier is that the verifier doesn't have access to the secret scalars and the blinding factors that the prover does, obviously. It only has access to the commitments that are given to it by the prover. But similarly to the prover, it gets these high-level variables, A, B, C, and D back, and then the same as the prover, it passes these variables and its constraint system into the toShuffle function, and then toShuffle function adds these constraints over the variables. And then lastly, it calls .verify with the proof, and only if the proof was a valid proof that all of the variables satisfy the constraints, and if the verifier's constraints match the prover's constraints, then will the proof verify correctly. So that's it. That actually is everything that's required to make this toShuffle gadget, and the code you can run the tests are at this link here. So just as a recap, these are the things that you can do using the Constraint System API. I illustrated the multiply, commit, and specify randomized constraints. Cool. So yeah, I talked you through the API for making multiplicative and linear constraints. I talked you through the protocol for making challenges, and then I showed you an example that illustrates both of those things. So that's cool and all, but it would be really great if we could build a system that's useful for blockchains with this. And so Chain and Interstellar have actually been trying to build a confidential protocol for a confidential assets protocol for a bit. There's been several different approaches, and we decided to build this with Bulletproofs. And just as a background, confidential assets are when you have multiple input and output items that have different asset types and different asset values, and you want to keep both the asset type and asset values confidential. So we wanted to build that using Bulletproofs. So first, we have sort of assembled a collection of gadgets that we would need in order to build this cloak protocol. So the different gadgets, and just as background, a gadget is a collection of constraints, and you can piece multiple gadgets together to make a constraint system. So the gadgets that we want are a shuffle gadget, which I just explained, basically proves that an output is a valid shuffling of an input. Also a merge, which proves that either the outputs are a merged form of the inputs, or that they were just moved without modification, and a split, which is the opposite of a merge, and then a range proof, which proves that a value is in a range, and so effectively you can think about that as a proof that a value is not negative. So in a cloak transaction with 3 inputs and 3 outputs, this is what a verifier or anyone viewing the blockchain would see. They would see that you have these inputs, they're shuffled in some way, they're merged in some way, they're shuffled again, they're split in some way, and then they're shuffled again to make the output ordering. And you can get a proof that the inputs, A, B, C, and the outputs, D, E, F, are a valid inputs and outputs for this particular constraint system. And you can do that without actually knowing how the inputs were split, moved, merged, but you can still verify that the proof is correct. So only the prover knows where the values are modified or moved, and they obviously have to know how they're modified or moved because they have to construct the proof. So walking through this as a prover, you know that the inputs are $5, 3 yen, $4, and you know the outputs. And your first step is to randomly order the inputs such that they're grouped by asset type. So now the dollars are next to each other. And then you merge all of the values that are of the same asset type together. And that gives you this, $9. And then you shuffle them so that the non-zero values are moved to the top of each asset type group. So hopefully you see where this is going, because we actually want to split all of the things that are non-zero into our target outputs. So here we know that our target outputs are 3 yen, $6, and $3. And so we split $9 into $6 and $3, and nothing happens with the other value. And then we add a last shuffle so that we can group, or we can order the assets in the order expected by the outputs. And then, of course, we have to do a range check, so we prove that nothing is negative, because that would be bad. So that's what the prover sees. And once again, as a recap, this is what everyone else sees. They get this, and they get a proof of validity. And transactions of the same size are indistinguishable. So anything with 3 inputs and 3 outputs are indistinguishable. So we have spec and code at this link here, if you want more information. So yeah, that's an example of how you can build a confidential assets protocol using a bunch of gadgets. And actually, one nice thing is that this is actually not much more expensive than making range proofs, just the range proofs. Because in the Bulletproofs protocol, the thing that's the most expensive is allocating multiplications. And the range proof takes vastly more multiplications than the shuffles, merges, and splits. And so this is actually like only a tiny bit more expensive than doing just normal confidential transactions, which doesn't mask the asset types. So that's pretty cool. All right, and so what we're working on now is ZKVM, which is a zero-knowledge smart contract. And basically the idea behind it is, what if we didn't restrict people to using only the gadgets that we build, such as like shuffle or confidential assets, but we make a language that people can use to build smart contracts in a customizable way such that they can prove whatever statements that they wish to prove over their values. So, so we're working on this with that goal in mind. Well, some background is that Chain, several years ago, made TXVM, which stands for the Transaction Virtual Machine, which was a new smart contract language that aimed to take the deterministic properties of Bitcoin, but also the expressive language of Ethereum, and combine those so that you can have like safe execution, but also expressiveness. And ZKVM actually just builds on a lot of the concepts of TXVM. We take a lot of the opcodes, we take a lot of the approaches, but we basically slap on this layer of like, now we have bulletproofs. And so now all of these things, instead of operating over plain text values, now you can operate over encrypted values and make a proof that the operations are valid for those encrypted inputs and outputs. So I think that's like actually pretty cool. The way we do this is by taking like these specific concepts. So from TXVM, we take the concept that values and contracts are linear types, and so they have laws of conservation. One example of what this looks like is that for values, which represent your financial values, you cannot create or destroy them without satisfying some very specific requirements. The only things that you're allowed to do are issue, retire, split, and merge, because those are the only things you should be allowed to do with your financial values in real life. So the same thing applies for contracts. You cannot just drop a contract, for instance. Also, contracts implement an object capabilities pattern, and the state updates via a deterministic transaction log, and the transaction log is actually generated by running through the transaction ahead of time. So it's not dependent on the state of the blockchain when you submit the transaction. And the thing that we get from Bulletproofs, by tacking Bulletproofs on, is we actually can make all of these operations happen over encrypted values and encrypted contract parameters. And then at the very end, you compile sort of the virtual machine code into like a Bulletproofs proof of correct execution. You can build contracts with arbitrary custom constraints, and you can protect asset flow with Cloak, which I explained earlier. So this is currently under development. This is the link that you can go to check it out. And so hopefully we have more exciting news to announce there once we are further along. Cool, so as a recap, all of this was built over the Bulletproofs proof system. We built range proofs, constraint system proofs, and using that we built confidential assets and zero-knowledge smart contracts. So I think there's a lot of other cool stuff that you can build using all of the tooling that exists here. And I'm really excited to see what else folks come up with. So yep, that's my presentation.
Awesome. Thanks. Yeah, really cool projects. So I have to ask, I would want to actually use a lot of this stuff as programming projects in our courses. Is it at the level where we could actually assign this as programming projects so students can build on top of?
Yeah, I guess just to sort of talk about like the stability of various pieces, our implementation of the range proof and constraint system proof, like those are relatively stable. Like they're not, like the API is not changing crazily. Same goes for confidential assets, but as I mentioned, the zero-knowledge smart contract, that's still in work, and so that's like changing every day. So I would like find that super fun.
Okay, cool.
Yeah.
And then also when you verify these, if you have to verify multiple transactions at once, do you take advantage of the batching capabilities?
We don't actually have batching implemented for the constraint system proofs, although you can. But we do have, I think we have batching implemented for range proofs. I haven't looked at that in a while. Yeah.
Because that's a significant speed up.
Yeah, it's a huge speed up, and it's definitely possible. Yeah.
Yeah, cool. Any other questions? Yeah.
Hi, I'm Matteo. Very nice talk. I have a question on the randomized constraint API. So a randomized constraint in your definition is something, a piece of the relation, a statement, micro statement that the prover can verify, can prove simply on a randomly sampled points. How does the API right now generate a check for the verifier that the point was sampled randomly?
Yeah, for sure. So actually, this is a great question because I can touch on like a lot of things that go into like how we know that for sure. One, so just to go back to the randomized constraint here. There, yes. What we do is we actually have, we call it a two-phase API. So there's a first phase in which you make commitments to your high-level variables, and then you also allocate some low-level variables. So in Bulletproofs, there's a difference between high-level variables are variables that you have like Peterson commitments to, and in the example of shuffle example, the high-level variables are like A, B, C, and D. And then you can also allocate some low-level variables. And then when you call the function like get randomized constraints or make randomized constraint system, what that does is that like basically transitions from the first phase to the second phase. And what that means is that it commits to all of the high-level variables, and it commits to sort of like a vector Peterson commitment of all of your low-level variables. And then, and this is like a really great tie-in to the previous talk, it puts all of those into the transcript, and it gets a challenge back from the transcript. And so that's what the prover does. On the verifier side, you actually pass the high-level commitments. You have to pass the high-level commitments no matter whether you're doing the randomized constraint system or not. But then in the randomized constraint system case, you also pass the vector Peterson commitment to the low-level variables that were allocated in the first phase. You give all of those to the verifier, and then the verifier does the exact same thing as the prover. They feed all of these commitments into the Merlin transcript and then get the exact same challenge back. And so to answer your question, you know it's random, or you know it's like deterministic based on these inputs because the verifier does that challenge construction, challenge generation themselves as well. And so you know that the prover could not have maliciously generated the challenge unless they're able to somehow like tweak the parameters in order to tweak the challenge, which would mean that they break the entire assumptions for this transcript in the first place. So.
Perfect. And it does sound like a use case for the Merlin API, actually.
Yeah, it's super great.
Cool. So it's actually using Merlin.
What's that?
It's actually using Merlin today.
Yeah, so our Bulletproofs implementation, and therefore everything above it uses Merlin.
Awesome. Great. Are there any other questions? All right. In that case, let's thank Cathie again.